introduction, we have an invited talk from Dr. Yana Jageska. Dr. Yana Jageska focuses on development of a new family of chip-scale trace gas sensors, which will replace bulky and costly instrumentation currently used to measure the tiniest quantities of gas. Originally from Slovakia, Yanas studied applied physics and electronics at the Czech Technical University in Prague and continued her scientific career towards a doctorate in photonics at EPFL, Switzerland. During her postdoctoral fellowship at EMPA in Zurich, she familiarized with spectroscopic methods for detection of greenhouse gases and air pollutants. And as a postdoc at UIT, she extended her expertise in optochemical on-chip detection. In 2016, she obtained a Frinatech Young Research Talent Grant from the Norwegian Research Council, and in 2017, an ERC starting grant to start her research group at the Department of Physics and Technology at UIT. In her research, she combines the methods of nanophotonics and laser spectroscopy to develop miniature but highly performant sensors for sensitive and specific detection of methane and isotopes of carbon dioxide. Her sensors can be, for example, deployed in drone conducted emission measurements in Arctic and also in industrial process control and medical diagnostics. And with this brief introduction, I would like to welcome Dr. Yana Jageska for her invited talk. Over to you, ma'am.
Thank you very much for the kind introduction. And let me just share the slide with you. Just if you can please confirm that you can see the presentation correctly.
Yes, yes.
Okay,
yes,
perfect.
Yes, we can see.
Great. So let me start. Thank you again for also inviting me and also introducing me so much in detail. And indeed, my talk will be about trace gas sensing with mid-infrared photonic waveguides. So before I start talking about the waveguides themselves, I will first try to say a couple of words about the Arctic University of Norway. It's not the most known university in the world, maybe, but it's definitely the northernmost university in the world. So as you can see here, it's located in the city of Tromsø in the very north of Norway, the city where we have northern lights in winter, 2 months of sunshine in summer where the sun doesn't set. And we have also this university. Here is just a picture of the building where I'm sitting right now, which this university is special in the sense that it is really located at the edge of the Arctic. And this location kind of governs the focus of the research, the strategy of the research of the natural sciences of the university, at least, which focus on the climate and environment. So this plot, which I'm showing here, it's a short motivation for my work. This plot shows the increase of methane in the background air concentration over last 2000 years, basically. So the blue points were recovered from ice core samples, while the red points here at the end were then measured from the air samples. What you can see, it's this continuous increase of methane concentration in the air, which is related to our the most burning issue of our generation, the climate change. So Arctic plays an important role in at least the emissions of methane, because there is a lot of methane which is stored in the frozen permafrost soils, and as the temperature of the earth increases slowly, this soil starts to melt and the methane is released into the atmosphere, contributing again to the greenhouse effect. But there are also special bacteria living in these soils which can consume methane. And part of the research at UIT is to figure out what will happen actually with the increasing temperature. If the release of methane will dominate, or this bacteria in the soils will get more and more activated and actually will consume methane or the excess methane from the atmosphere. So yeah, for this task, they need also sensors. The sensors needs to be specific. They needs to be sensitive enough to be able to measure these small increases on the background of the concentration of existing methane or existing concentration of methane in the air. And last but not least, this sensors needs to be easy to be transported to those remote locations of the Arctic. So what we would like to have are small sensors. Yeah, by the way, this is one excellent group, CAGE, which is studying the gas hydrate and methane emission at UIT. But yeah, back to the sensors. The sensor research, the research on chip sensors started about 2009 in UIT by my colleague, Professor Olav Gaute-Hellesø, whose group I joined in 2015 as a postdoc, and 2 years later I started my own group, which, unlike Olav, who was focusing on refractive index and chemically sensitized sensors, I focus on photonic detection of trace gases using a spectroscopic method, and in particular laser absorption trace gas spectroscopy. So what are again those trace gases? According to the definition, trace gases are all gases found in the air which have less concentration than 1%. So they are actually all gases except for nitrogen, oxygen, and sometimes water. So the most important trace gases in terms of climate change are carbon dioxide and methane, and these are also the gases we mostly focus on, including their isotopes. So there is already a variety of sensors, from the smallest to the largest, from the least sensitive to the most sensitive, which are suitable for the task of trace gas detection. And they are also, most of them are commercially available, and they are also often deployed. However, you can see that if this is the axis which shows the sensitivity of detection, starts about percent of the gas here to ppt, which means part per trillion, or one molecule among 10 to the 12th of other gas molecules, we can sense gases in this full range. But as we increase the sensitivity, the size of the instrument and also the price of the instrument very much increases. So our purpose is now to keep the size of the instrument at this level, at the chip level, but get much better in terms of sensitivity and specificity. Specificity means that we are really sure that the gas what we are measuring, or the response of the sensor, is due to the gas we want to measure, and that the sensor also doesn't lose its specificity over time, so it doesn't exhibit drifts or degradation over lifetime, which is not too long typically. So what we want to do is to develop this type of sensor, sensor on a chip, which will be able to measure somewhere between part per billion and part per million concentration levels, which are exactly the detection limits necessary for quantification of emission from different sources, measured against the background atmospheric levels. So how does this typical high-end laser spectrometer look like? it is based on a pretty simple setup shown here, consisting of a laser, a multipass cell, and a detector. The multipass cell is the part of the sensor which is typically the largest, actually, because the laser and the detector already are on-chip devices. And in the sensor, the interaction between the light and the gas molecules takes place. So typically, we have the laser, which is shined into the multipass cell. The multipass cell is made of two specially curved mirrors where this laser beam is reflected many times, traveling a very long path length of sometimes even 100 or 200 meters. And the longer the interaction path length, the higher the probability that some of the photons in the light will interact or will find our scarce molecule of the gas which we want to detect. And it will, so the longer the path length, the stronger the absorption signal from this molecule. So then the laser is typically tuned across a couple of nanometers or wave numbers, as we spectroscopic speak in wave numbers instead of nanometers. And yeah, so the laser is tuned and the transmission response after the multipass cell is then measured by a detector. The detected spectrum may look like this, where we see that for different components, in this case, an example is shown for methane and water, we know exactly at which location, like here, for example, for methane, we have two peaks. So we know at which location, at which frequency the absorption takes place for methane, and at which location the absorption takes place for water. So from the frequency or the position of our transmission peaks, we can say something about the composition of the gas we have in the multipass cell. And from the depth of those peaks, we can recover the information about the concentration. So now, if we want to do the same on a chip, as I said, laser and detector are already on-chip devices. We need to replace this part, the multipass cell, which is the only really bulky part of the instrument. And we want to replace it by nanophotonic waveguides. So as you know, then in nanophotonic waveguides, the light travels in form of confined modes in some kind of channels, which can be lithographically patterned on the top surface of a chip, like shown in this image here. And the light will follow this pattern, and part of the light can escape the material and interact with the surrounding environment through the so-called evanescent field here. So the final vision for this research is to develop a structure which looks like this, which contains either monolithically or heterogeneously integrated laser detector with the sensor chip and possibly some on-chip pumps, which will be able to either decrease the pressure here to have even higher selectivity or just to maintain the flow of the gas through our specimen. But if we want to use these nanophotonic waveguides instead of our multipass cell with free space beams and in very, very long path lengths, we have really a couple of challenges to face. So first of all, we need to develop long and low loss waveguides. That's nothing new in the photonics world. There are actually quite a few waveguides, integrated waveguides, which exhibit very low losses, and they could achieve a couple of or more than a couple of meters, like in this particular example, which I'm showing from Li et al. They achieved 7 meters of waveguide with the loss of 0.08 dBs per meter. So it's extremely low loss waveguide. This was in silica. Or another example shows more than 3 meter long waveguide with a loss of 0.7 dB per meter, realized in silicon nitride core cladded by silica. Yeah, so in both these cases, the waveguide losses were extremely small, and they are almost, not really, but they're going in the direction of optical fibers, which can exhibit propagation over many, many kilometers. So it is possible to create low loss waveguides on a chip. However, as you can see in both these cases, it can be seen even better in the second image. The waveguides were designed such that all the optical field is actually confined in the material. And this is also the reason of the low loss, because it doesn't see any edges, it doesn't see any boundaries, any walls where the light could scatter and exhibit propagation losses. So our challenge now is to develop low loss waveguides, but with high evanescent field confinement. So this part of the field which can interact with the surrounding medium should be substantial. Also, another challenge is to extend the operation of those low loss waveguides to the mid-infrared. So all these waveguides, they work at telecom frequencies, but the spectroscopy and the gas sensing is the most sensitive in mid-infrared, where the absorption is about 2 orders stronger, 2 orders of magnitude stronger than the absorption of the same gas species in the near infrared. So one example of photonic waveguides, which has been already used for sensing and methane sensing, is this very standard silicon or SOI strip waveguide. If properly designed, it can give optical field confinement of up to 25%, meaning that this evanescent part of the field is resulting in interaction which is about 1/4 of the interaction of the free space beam. Which also means that if we want to have the same sensitivity as the free space beam, we need to make this waveguide 4 times longer. So that's definitely a little bit of disadvantage. And there are also more disadvantage of these designs, which is rather high scattering loss from the sidewalls, which will not be below 1 to 2 dBs per centimeter in the near infrared, and the situation gets even worse in the mid infrared because this waveguide is typically sitting on a silica bottom substrate or bottom cladding, which start absorbing as we approach mid infrared wavelengths. So we need to look, I just can add that with this waveguide, probably the best methane integrated on-chip sensor has been reported. That's the work of IBM, and they were able to demonstrate a 10 centimeter long waveguide of this type. And they were able to detect down to 100 ppm methane after 1 minute of averaging. So 100 ppm is still very far from what the high-end spectrometers can do, but it's, I think, a very fine work and a good start and good reference for us. Well, what we want to do, we want to use special designs of waveguides, which will be optimally suited for the task of gas detection. So one of those is the slot waveguide. It's quite well-known waveguide, which consists of two strip waveguides closely spaced, separated by a slot. And if the dimensions of those strips and the slot are chosen properly, the TE polarization will end up being localized, or the majority of the optical field end up being localized in the slot, in the air slot between the two strip waveguides, which can exhibit then the optical field confinement or the interaction with the surrounding air larger than about 70%. But we still keep high loss due to sidewall roughness and scattering, and we still keep the SiO2 absorption in the mid-infrared. So the design which I would like to talk about for the rest of my presentation is the design showing here, design of a freestanding Rib waveguide, which was developed and recently reported by my group. So this design, as I will show later, can exhibit optical field confinement, which is more than 100%, meaning that the light interaction with the surrounding gas can be stronger than in the free space beam, which sounds a little bit controversial, but as I will explain on the other slide, it's physically perfectly possible. This design also removes the bottom cladding. So the evanescent field is both on the top and the bottom side of our waveguide membrane. So it doesn't exhibit any substrate absorption. And the design based on Rib waveguide also induces very little scattering losses, and they contribute negligibly to the propagation loss. So the idea behind the design is that if we can produce a membrane waveguides like shown here, the evanescent field will extend both above and below the membrane almost symmetrically. And then if we are decreasing the thickness of the membrane, this extent of the evanescent field will increase. So if we now look at how the interaction between the gas and the light is defined, we can first think of free space, where we know that as the beam propagates in an absorbing media, the intensity will be exponentially decaying along the propagation direction according to this Lambert-Beer law, where alpha is the absorption coefficient of our medium and L is the length of the interaction path length. In the waveguide, we can write this formula in a very similar way, where we use this gamma as a constant, which is scaling the interaction due to the fact that some of the field cannot interact with the gas. So this will be the confinement factor I was talking about. This confinement factor is defined by this equation, where here on the right-hand side we have overlap integral of the electric field energy. So we calculate the electric field energy in the cladding material or in the gas where the light can interact by dividing by the total electric field energy in the propagating mode. And what is important, we cannot forget to multiply this by a group index of the propagating mode scaled by the cladding index, which is in our case air, so equal to 1. So what is again important is the group index and the overlap integral, or the evanescent field ratio of the optical mode. So in our waveguide, if we want to simulate this gamma, the confinement factor, for both TE and TM polarization as a function of the thickness of the membrane, we get the following plot. So as the layer is increasing, we see that for the TE mode, which is quite well localized in our membrane, the air confinement factor is decreasing monotonously. But for the TM mode, the confinement factor increases, and in a region of up to about 500 nanometer thickness of the membrane, it is actually larger than 100%. This is due to the fact that both the field is very strongly delocalized around the membrane, so we have a large majority of the field both above and below the membrane, and also through the fact that we have some contribution from the group index, which is larger than 1. So both the product of the overlap integral and the group index of the waveguide will give us theoretical confinement factor of approximately 108%, about 350 to 400 nanometers. So this sounds already very promising, so let's fabricate those waveguides. We fabricated these waveguides in the according to the following procedure, and here I also have to acknowledge my two colleagues, my PhD student, Marek Vlk, who did most of the fabrication work, and my dear collaborator from UK, Senthil Ganapati Murugan. The fabrication, we started by depositing a tantalum pentoxide layer. So the choice of the material is not so crucial, but it should be transparent in the mid-infrared, which tantalum pentoxide is, and it should also exhibit rather good mechanical properties. So we started with tantalum pentoxide, about 350 nanometer thick layer, where we patterned first the Rib waveguide by means of standard UV lithography. The Rib height is about 30 nanometers, so actually quite little, and so that it doesn't induce too much scattering, especially not in the mid-infrared. And we also took care to have the size of the Rib not exceeding the size for single mode waveguides, so that we can produce single mode Rib waveguides in both TE and TM polarization. In the second step, we patterned this kind of holes alongside the Rib waveguides, which are located quite far away from the Rib, so they shouldn't be seen by the optical mode, but they are there for the purpose of under-etching of the membrane. So after patterning the holes, we came with etching agent, which we tried a few of them. What worked the best were either the xenon difluoride or SF6, and we could effectively remove the substrate from below the membrane. So here, this is how it looks in reality. With different etchants, we have different profiles a little bit, but in any case, we always end up with a very thin, like this hairline is this thin tantalum pentoxide membrane, which is separated at least 10 micrometers from the silicon substrate. The top view of the membrane is shown here. So on this cross section, you cannot see the Rib waveguide because it's very, the Rib is only 30 nanometers and very small. However, in the optical microscopy image, you can see already the contrast. So this is the Rib waveguide. Here are the etching holes. And here you see the boundary of the under-etched membrane. So the membrane extends from here to here. And the location of the optical field is just indicated here. So there should be, or there is, as we confirmed in the experiment, enough space between the bottom silicon substrate and the extended optical mode. The fabricated chips were fabricated in different lengths and configurations. So we were looking also into those spiral designs to be able to pattern the longest possible waveguide on a small chip. However, we realized that at this point, due to the material problems, we were still limited to just a couple of centimeters for the propagation. So these chips look fancy and the design will be recycled now, but unfortunately, until now, we were able to really work only with straight waveguides. So how did we characterize these waveguides? The basis was this setup. And the guys I have to thank for the work are postdoc Anurup Datta and again my PhD student Marek Volk, both members of my team at UIT. So in the setup, we are using a laser diode emitting at 2566 nanometers in mid-infrared, which is focused by an aspheric lens onto our chip, which is sitting in a specially designed environmental gas cell. And then this laser can be tuned across something like 7 nanometers. And the transmission is detected on the other side, on the output from the chip by the mid-infrared detector. So here just a little bit detailed look on the gas cell, which contains the optical chip. It has mid-infrared transparent windows on both sides, and we know exactly the extent between the window and the chip on both sides. And we also have another window on the top to be able to see the chip from the top to facilitate the light in-coupling and also the measurement of the loss. So we have a mid-infrared camera looking from the top through this window to see what is happening on the chip. Oh, I think that I skipped one slide. In any case, there are also the two mass flow controllers, which can mix, in our case, acetylene, which is a gas which has absorption at this, like a strong absorption peak, rather strong absorption peak at this wavelength. And by these two mass flow controllers, we can mix the concentration of acetylene and nitrogen as much as we want between basically 0 when we flow only nitrogen and 10% of acetylene, which is the concentration in our calibration gas cylinder. And yeah, we can fill the volume of this flow cell with the design concentration of the gas. So yeah, when we want to characterize the losses, we use the fact that despite this waveguide scatter very little, our camera is so sensitive that we can still see the scattering along the waveguide, which is this line, this middle line here. And there also some scattering from at both sides of the line. So this is some scattering from the etching holes. And yeah, so if we now follow the decay of the intensity of this central line from the waveguide, we can quantify the propagation losses in both TE and TM polarization. So here they are the numbers and the intensity decay plotted as a function of the distance from the input facet of the chip. And we had to conclude that the losses in this particular case are rather high. So they are smaller for the TM polarization, actually for the one which has this great evanescent field confinement, and the loss is about 7 dBs per centimeter, while for the TE polarization, the losses are almost reaching 40 dBs per centimeter. So this waveguide here is extremely lossy in TE, but quite reasonably lossy in comparison to other mid-infrared waveguides in the TM polarization. So the propagation loss at this wavelength results from or can result from several effects. The first is the most trivial, the scattering loss, but we concluded that actually this one is still pretty negligible, because if we measure this loss in near-infrared wavelengths, we have only something like 2 dBs per centimeter. So we would expect, since the losses are scaled like 1 over lambda to the power of the fourth, we would expect much higher losses in the near-infrared if the scattering really was the main issue. So we can kind of rule out the scattering as a substantial scattering loss source. Then we have another issue, which is a lateral leakage of the TM mode. This can be, if the waveguide is properly designed, this TM mode can be, or this lateral leakage of the TM mode can be almost zero. However, if there are some discrepancies between the theoretical and real dimensions of the waveguides or the refractive index values, we still can get some leakage, and we estimated this leakage to be about 1.5 dBs per centimeter or so. Still, the largest contribution to the loss is unfortunately from the absorption loss of the material in the mid-infrared. Even the material itself should be perfectly transparent. It turns out that our material, which we deposited, had some kind of columnar structure, which can incorporate water molecules or these OH bonds. And these are those which start absorbing at the mid-infrared. So to decrease the absorption, we need to pay a bit more attention to the material optimization of the deposition processes. It is also quite nice to see that this material absorption obviously scales with the confinement of the optical field in the waveguide core. So while the TM mode is mostly in the air and it has only 9% confinement in the core, in the material, the TE mode has 77% confinement in the material, and therefore the absorption is much stronger for the TE mode than for the TM mode, which explains the results here. So as I said, due to this problem with the absorption and with our material, we had to limit the waveguide length to 2 centimeters. And the challenge to address in the future is to remove this absorption and go longer. So yeah, this was for the loss characterization, and now for the spectroscopy characterization. As I said, we have a rather strong peak of acetylene at about 2.66 nanometers, which coincide with the central wavelengths of our diode laser. And if we scan now the transmission through the waveguide or through the free space, which are filled with some concentration of acetylene, we should be able to recover this absorption peak. So these two plots show the transmission spectrum upon tuning the laser when we didn't have the waveguide in the cell, but we had the beam going through the cell filled here with nitrogen or 0% of acetylene. In here, it was 10% of acetylene. So we see that at this location, we got a transmission peak, which corresponds to the acetylene peak or the presence of acetylene. So if we have a closer look at the peak, it is shown here. And now when we put the waveguide into our gas cell and do the same measurement, we can recover almost exactly the same peak, but you can see that it goes a little bit deeper here. So then we used to fit both spectra with a database spectra from the PNNL database. for different concentration, and we got this plot on the left. So each time we could, from the depth of the absorption or the transmission peak, when we fitted it, we recovered the concentration of the gas. So for the free space, as expected, the concentration was given by the slope, showed by these red points here, are corresponding to the free space concentration recovered from this fit. And they correspond to 10%, which gives us the confinement of 100% in free space as expected. When we did the same with the waveguides, the measured concentration were always slightly higher than the concentration in free space, and the fit gave us the slope of 1.07, which results in the experimental confinement of 107%. So with this measurement, we could indeed confirm that the interaction in our waveguide was higher than in free space, and this 107 confinement factor very well corresponds to our theoretical 108, which we got from simulations. We also then looked into the lowest possible concentration which we can detect with these waveguides, and also in free space, just to compare the how the performance of the waveguide sensor. So we measured the concentration over more than 500 seconds, and then we calculated the Allen deviation, which is the standard deviation as a function of averaging. This plot wants to say that the limit of the deviation and the limit of detection decreases if we average, obviously. And after 25 seconds of averaging, we were able to determine this detection limit of 7 ppm with the waveguide and about 3 ppm in the free space. So that was the capability of our setup, and this was the slight deterioration due to the fact that we had the waveguide. So with the waveguide, even though the interaction is slightly stronger, we are still slightly worse, but this result is, as I wrote here, better than ever, because this is the first time which we, with a waveguide device, we approach the detection limit of a comparable free space measurement to such an extent. So we are almost there. We also see that the main problem here is the noise at short integration times, where the two curves have the largest discrepancy. And this is due to the fact that we have some vibrations in the setup, and then the coupling is causing the additional noise. We are using free space setup. Upon integration, the situation should improve somehow, and then the performance of the waveguide can be really comparable or identical to the performance in the free space. Not to mention that if we manage to decrease the propagation losses, we will be able to pattern much longer path lengths on a very small footprint. Yeah, so we had the comparable stability for longer integration times. This brings me to the conclusion that our freestanding membrane waveguide is special in the sense that it supports almost free space-like guided modes, which have a very high evanescent field confinement in the air. They exhibit exceptional interaction between the air and the light, or the optical modes. And they also exhibit low spectral noise due to reflections one of the main problem in integrated devices is that the transmission normally has a lot of reflections due to the facet reflections or reflections on the defects. However, since the mode here is so much in the air, the effective index mode is so close to the air that this reflection almost don't occur or are not really measurable. So this waveguide has a series of, or a set of really good properties for laser absorption spectroscopy. The next challenges are to increase the length, to decrease the material absorption, and also to try to work at even longer mid-infrared wavelengths to access the even stronger absorption bands of the different gas molecules. We are currently working on this last task, the development of prototype for first field applications. So most of the story I was telling you today about this freestanding waveguides is summarized in this paper, which we got recently published in Light Sciences and Applications. In the future, or even currently, we are looking also into other waveguides and other ways how to measure gases using integrated on-chip sensors. As I said, we are also using the slot waveguides, but we are also looking into this type of waveguides, which are porous waveguides, which exhibit interconnected network of pores directly in the waveguide core, and the gas can penetrate inside the core and have this interaction directly inside the core of the waveguide. And we are also going to study the photonic crystal waveguides, which exhibit slow light and interaction increase due to the slow light. So if you are interested in our research, I can direct you to the project site here, or you can simply write me an email, contacted me on this address, Jana Jagers, KUITNO. And with this last slide, I would like to thank you for your attention, and also I would like to acknowledge my whole team. This is the Tromsø section in the top row, and these are all my collaborators from UK, NTNU in Norway, Germany, and my previous supervisor and dear colleague Olav Gaute-Hellese. And I also would like to acknowledge the funding from the mentioned funding agencies. So thank you very much for your attention, and now I will finally reply your questions.
Thank you, Dr. Jageska, for a wonderful talk on this afternoon. So we have a couple of questions, and I will read it out for you. So can mid-IR plasmonic materials like gallium phosphide and gallium nitride be used to increase the evanescent contribution?
I don't see the reason why not.
Okay.
But I mean, I don't see a reason why they could not be used if they are mid-infrared transparent, but I don't see how they should increase the evanescent wave contribution. Maybe if they have a slightly higher refractive index, they could even increase in the same design the evanescent wave contribution, but this will be quite comparable. So the evanescent field contribution is not so much material dependent. It is slightly material dependent, but it's mainly design dependent.
Okay, thank you. And another question is, is the dynamic range of the acetylene? So what is the dynamic range of the acetylene sensor?
So the dynamic range is it can be probably something like 1,000 ppms. So, but the advantage of, normally the dynamic range is given by the the range of concentrations before we started saturating on one side, and on the other side we still need to have a stronger signal than the noise. So with this sensor we typically can measure from a couple of, basically from 100% with these short sensors to down to 7 ppm. So it's about this 1000 ppms. But what we can do in the future, we can on the same chip implement different lengths of the sensor from the shortest to the longest, and we can thus effectively extend the range by the chip design. So we can have several channels where the light is split into with a couple of detectors, and based on the concentration which we measure, we can select the right channel and basically measure in the full range of concentrations. So that's the advantage of the on-chip design.
Okay. And there is another question. Is there any particular concentration of methane that's considered to be harmful or toxic?
Harmful or toxic? Not really, but is explosive. So we normally can work with up to 4% of methane concentration in our labs. And this is the same thing in the mines, for example. So if the concentration increases over 4%, and there is a spark, it can explode. So that is the main concern. And of course, if the whole air is filled with methane, we cannot get enough oxygen. So but generally methane is not toxic. And all these concentrations, which I was talking about, up to 4% are safe to be used in laboratories.
Okay. And another question, can a broadband source be used instead of a single laser to detect multiple gases?
Broadband source can be used. However, the broadband source requires a spectrometer at the output, either so that we have this spectral, we need to know our spectrum. So we either have a narrowband source and we tune it and one pixel at one point detector, or we have a broadband source and the spectrometer at the output, which might make the design more complicated. So there are, of course, designs of on-chip spectrometers like recently, even in the mid-infrared. However, the resolution is not satisfactory currently for working with gases. So in this sense, the single mode laser is preferred, but there is one particular broadband source which can be used, which is optical comp. So you can already use optical comps in dual comp spectroscopy, which can give you exactly what you want, the detection of gases in a broad range. And these are also currently being fabricated on a chip. So definitely in the future, yes.
Okay. And another question, is there any possibility to increase the sensitivity by increasing the number of slots in the rib of the waveguide?
The number of slots, yes, but the improvement is marginal. I think that the group from Belgium has demonstrated that if they used a coupled slot waveguides, they could increase a little bit the interaction. But it's really something which is maybe not worth the effort, I would say. So I think that it's best just to tune the design with the one slot or one rib that you have. And there are all these other effects which can increase the interaction much more, like the increasing the group index in the slow light regime, for example.
Okay, so once again, thank you, Dr. Hiana Jageska, for giving a wonderful talk on in this international conference. And we are extremely thankful for accepting our request to give this talk. So thank you for your talk.
Yeah, thank you very much again for the opportunity to give this talk. And I hope that it was interesting for you to see what we are doing. And I think that we will also have a PhD position later this autumn in the group. So if there are any students interested in the PhD, just please contact me on the given address.
Yes. We will definitely pass on this to our students.
Then I wish you a good afternoon.
Thank
And
you.
I will continue with my morning here in Europe. Bye-bye.
Okay, bye. Thank you.
Bye, Yana.
Bye-bye.
We are extremely thankful to you, ma'am, once again for giving us such a beautiful talk. Thank you so much. I would also like to thank Assistant Professor